This is the outline of my presentation. Introduction of optical fiber. Optical fiber made by glass or plastic. Waveguide having core and cladding. Light traveling the central or core surrounding by cladding. Guiding technique total internal reflection. This figure shows the optical fiber. This point is core, this figure is cladding, and white portion is coating, and outer side is outer jacket. Hollow core fiber. Hollow core fiber propagate light with a hollow region. Basically, two types of hollow core fiber. Hollow core photonic band gap fiber, hollow core anti-resonant fiber. Hollow core photonic band gaps have limited transmission bandwidth, but hollow core anti-resonant fibers simpler cladding design and ample transmission bandwidth. Compelling properties: low transmission loss, good bandwidth. This figure shows the hollow core fiber figure. Hollow core anti-resonant fiber. Hollow core anti-resonant fiber effect for transmitting the light. There have two band region, resonant region and anti-resonant region. Hollow core anti-resonant follows inhibited coupling mechanism. Core mode inhibited coupling with the cladding mode. This figure shows the hollow core anti-resonant fiber for cross-section. Terahertz system. Terahertz system wave range from 30 micrometer to 3 millimeter and lies between microband for infrared radiation. Terahertz wave maintains a predictable polarization state of the guided mode by high birefringence. Applications are medical imaging, spectroscopy, safety, security and safety, imaging, communication, etc. This figure shows the terahertz system. High birefringence hollow core anti-resonant terahertz fiber. In this paper, measure achievement high birefringence 7 cos 10 to the power 4 in the frequency range from 1 to 1.24 terahertz. The total loss is the sum of the confinement loss and effective material loss. Total loss value in this paper 0.0168 decibel per centimeter. Shortcomings: higher total loss performance, lower birefringence, structure intricate enough. Low loss polarization maintaining hollow core anti-resonant terahertz fiber. In this paper, measure achievement a high birefringence of 1.52 cos 10 to the power 4 at 0.9 terahertz. The total loss performance 0.1 dB per centimeter. Shortcomings: complex structure, birefringence is not good enough, the total loss is not good. This figure is schematic cross section of the proposed terahertz hollow core anti-resonant fiber. The design of polarization maintaining and polarization filtering hollow core with nested anti-resonant nodeless fiber for terahertz guidance. In this paper, measure achievement a high birefringence of 1 cos 10 to the power 4 operating at 1 terahertz. The total loss is 0.01 dB per centimeter. Shortcomings: structure intricate enough, birefringence is not good. Multiple design with broad applicability for enhancing birefringence in low loss terahertz hollow core anti-resonant fiber. In this paper, measure achievement a high birefringence 1.2 cos 10 to the power minus 3 at 1 terahertz. A minimum loss of 0.2 dB per meter. Shortcomings: structure is complex, birefringence is not good. Summary of research gaps. Most of the low loss fiber structure have very complex design. Active birefringence level is not good enough. Limited transmission and bending loss performance, narrow operating bandwidth and weak signal mode performance. Objectives of research: to design an original and simple cladding in fiber structure for terahertz region, to achieve a high birefringence over a broad bandwidth, to achieve a very low confinement, effective material and bending losses to perform as a single mode fiber. This figure is our proposed model. This proposed model cross-sectional image of the fiber with following dimension of core diameter 3 mm, outer circle diameter D naught 0.96 DC, linear similar location D in 2 mm, outer circle location D at 3.135 mm, and 3 thickness are T1 and T2 are the topmost thickness and T aluminum thickness. Respectively, the red region, the red portion is represented by aluminum coated region. White region is the air, and blue region is the topaz material, and gold material represent the PML layer. Methodology: design and simulation console multiphysics, data collection Microsoft Excel 2019, calculation and analysis MATLAB 2016 and Visio 2019. Design structure with proper parameter in console multiphysics, compute through finite element method that manipulated by Maxwell equation. Finally, analyze the studies data. This is a basic theory. Various formulas are used, which are given below. Result and discussion. This figure shows the electric field profile. Black arrow indicate the direction of propagation. Figure A, X-pole ray passes through the core, and figure B, Y-pole ray couples with the clouding. Effective RI, refractive index and birefringence analysis with respect to the frequency. In this figure, X-pole represented by frequency and Y-pole represented by effective RI. In this figure, frequency varies from 0.5 terahertz to 1.5 terahertz. In this figure, we can obtain high bioreference value 1.38 cos 10 to the power 3 at 1 terahertz. Higher than 10 to the power 4 of bioreference is maintained over 0.8 terahertz to 0.5 terahertz to 1.3 terahertz. Loss performance. Loss performance represent with respect to frequency. In this figure, confinement loss of 3.14 cos 10 to the power 5 decibel per centimeter at 1 terahertz for X-pole ray. Confinement loss of 8.99 cos 10 to the power 4 decibel per centimeter at 1 terahertz for Y-pole. Effective material loss. Effective material loss of 9.79 cos 10 to the power 4 dB per centimeter at 1 terahertz for X-pole. Effective material loss of 3.39 cos 10 to the power 2 dB per centimeter at 1 terahertz for Y-pole ray. Total loss and PR performance with respect to change in frequency at x-axis. In this figure, we can obtain par and total loss. Total loss of 1.01 cos 10 to the power 3 dB per centimeter at 1 terahertz for X-pole. Total loss of 2.3 cos 10 to the power 2 dB per centimeter at 1 terahertz for Y-pole. In this figure, at 1 terahertz, this result in PR of 35.39 dB. Bending loss performance with respect to frequency. In this figure, we can obtain bending loss at 1 terahertz fixed. In this figure, change in bending radius. or bend radius. Bending law in this figure we can obtain bending loss of 8.2 cos 10 to the power 3 dB per centimeter for bend radius 10 centimeter. Bending loss 6.62 cos 10 to the power dB per centimeter for 13 centimeter. Bending loss of 9.12 cos 10 to the power 4 dB per centimeter for bend radius 24 centimeter in this figure. Single mode performance. In this figure shows the single mode performance. Single mode performance has one of fundamental mode FM or LP01 and 3 higher order mode of LP11, LP21, LP02 are considered in this figure. LP11 is the lowest loss among HOMS. Humor of 35 dB is found of 0.35 terahertz. Humor of greater than 10 is acid from 0.8 terahertz to 1.15 terahertz. Comparison study. Relative study on proposed and existing fiber. In this column here, in this column structure, in this column total loss, in this column Humor, or in this column by references. 2018 in paper published and structure holocaust 10 tubes, and in this paper we can obtain loss 0.168 dB per centimeter, and in this paper no Humor, and in this paper we by reference value 7 cos 10 to the power 4. In 2019 HC4 half elliptical, and in this paper 0.1 dB per centimeter, and there is no Humor, and by reference value 1.52 cos 10 to the power 4.
Please speed up the presentation. সময় 12 মিনিট চলে গেছে, একটু দ্রুত শেষ করলে কনক্লুশনের দিকে গেলে ভালো হয়।
Fabrication feasibility study in this 3D printing method. Conclusion. The proposed fiber provides a new and simpler anti-resonant fiber with aluminum coated layer based semicircular cladding structure by reference of 1.38 cos 10 to the power 3 at 1 terahertz and greater than 10 to the power 4 level maintain over 0.8 terahertz. Lower confinement loss of 3.14 cos 10 to the power 5 dB per centimeter is obtained at 1 terahertz. Minimal effective material loss of 9.79 cos 10 to the power 4 dB per centimeter is found at 1 terahertz. Minimum bending loss of 6.62 cos 10 to the power 4 dB per centimeter is achieved for 13 centimeter bend radius. Humor is greater than 10 over 0.35 terahertz along with highest Humor of 35.
Thank you for your nice presentation. We have only 1 minute, so we can take one question from the audience.
Okay, if there is no one, then I have a question to the presenter. Is there anyone else want to ask question? Or I from the chair will ask a question to Sagar Ali. Okay,
sir, I don't think there is any question, so you can ask.
Okay, Mr. Sagar, what is the point of coating with aluminium? It is not clear from your presentation. Can you explain a bit more?
We can use aluminum coated layer because birefringence increase and loss reduce.
Okay, so all the hollow cores will be coated with aluminium or just only one, as shown in the figure? বুঝুনি, আমি বললাম যে সবকটা করি কি ভিতরের দিকে অ্যালুমিনিয়াম কোটিং দেওয়া হবে না, যে একটা তুমি দেখিয়েছো যে সেটাই মাত্র, কোনটা হবে সেটা?
জি স্যার, আই ক্যান নট, স্যার আমি বুঝতে পারি না এটা।
আমি বলছি যে হলো কোরের ভিতর তো অ্যালুমিনিয়াম কোটিং দেওয়া হচ্ছে। তো
জি স্যার।
ফিগারে তুমি দেখালে একটা কোটিং, একটাতে দেখালে যে লাল লাগে, এটা হচ্ছে অ্যালুমিনিয়াম কোটিং। এটা কি সবগুলো হলো কোরের মধ্যেই থাকবে না শুধু একটাতেই থাকবে?
স্যার এটা তো
আহ,
আমরা ব্যবহার করছি হচ্ছে আমাদের, মানে আমরা এই ডিজাইনের জন্য শুধুমাত্র আমরা স্যার এটা ব্যবহার করছি।
হ্যাঁ,
আর
আমি তো এখানে
একটাতে
তো
স্যার দিলে আমরা
কয়েকটা
এখান থেকে
হলো
স্যার,
কোর আছে না, মাঝখানে একটা আছে, চারিদিকে
স্যার
অনেকগুলো।
একটাতে দিলে শুধু স্যার আমরা বেশি বাইরে ফ্রেন্সেন্সের ভ্যালুটা পাচ্ছি স্যার, একটা সার্কেল ইয়া
আচ্ছা,
দিলে। আর
আমি
এটা স্যার অ্যাসিমেট্রিক্যাল
তাহলে
ডিজাইন।
তোমাদের প্রপোজাল হচ্ছে শুধু একটাতেই থাকবে।
জি স্যার।
আচ্ছা, তাহলে তো প্রশ্ন আসছে এটা কোনটাতে থাকবে, বা এর ওরিয়েন্টেশনের উপরে কোনো ইফেক্ট আছে কিনা।
স্যার বুঝি নাই।
আমি বলছি যদি একটাতে থাকে, তোমরা কি সবগুলোতে করে দেখেছো? ওখানে 6টা আছে মনে হয়, সম্ভবত 6টা কোড আছে, তাই না? ওরকম হলো কোড আছে 6টা। যাও ফিগারে, যাও ফিগারে, যাও ফিগারে। না, 1 2 3 4 5টা আছে, 1 2 3 4 5টা, একটার মধ্যে দেওয়া আছে তোমার অ্যালুমিনিয়াম কোটিং।
জি স্যার।
মাঝখানেরটা হলো এই যে ডিসি যা হচ্ছে, এটাও তো আসলে এয়ার আছে এর মধ্যে, তাই না? এটাও একটা হলো, একটা কোড। তো এ শুধু একটাতে দিয়েছে, তো অন্যগুলোতে দিলে কি ইফেক্ট হয়, এটা কি
স্যার
ভেরিফিকেশন করা
আমাদের,
হয়েছে?
স্যার এখান থেকে স্যার আমরা যদি ম্যাটেরিয়ালটা সবগুলোই ব্যবহার করি আমরা স্যার, তাহলে তো আমাদের কস্ট ইফেক্টিভ হয়ে যাবে। আর আমরা স্যার একটাতেই অ্যালুমিনিয়াম ব্যবহার করে স্যার আমরা বাইরে ফ্রেন্সেন্সের ভ্যালুটা বেশি পাচ্ছি, এই জন্য স্যার আমরা একটাতেই ব্যবহার করছি।
আচ্ছা, ঠিক আছে, ঠিক আছে, ওকে, থ্যাংক ইউ ফর ইউর প্রেজেন্টেশন, এন্ড আই হোপ ইউ উইল
আচ্ছা,
ডু বেটার ইন ইউর ফিউচার ইউনিভার্স। থ্যাংক ইউ।
আসসালামু আলাইকুম স্যার।
Acha, thank you for your presentation. Our next presenter, paper 38, simulation and numerical analysis of triple absorber solar cell using SCAP 1D. I can see Mahmoud Suyod.
Yes,
Uh,
sir. I'm present, sir.
okay, could you share your slide? And Mr. Shagor, could you stop your slide share? Yes, now Mahmoud Suyod, please share your slide and start your presentation. Thank you. We are already like, so please. পেপার 38 স্লাইড রেডি থাকলে একটু শেয়ার করে শুরু করতে হবে। অলরেডি
Give me a
11:48।
second, sir. Sir, can you see my screen?
I am not seeing any screen or any presentation slide.
Sir, can you see my screen?
Not yet,
না,
not yet.
Sir, I have unstable net.
I think it will come soon.
স্টার্টেড স্ক্রিন শেয়ারিং, স্লাইড এখনো দেখা যাচ্ছে না।
Sir, am I audible, sir?
Yes, you are.
Sir, I'm joining from mobile, so I will show from mobile.
We can hear you loud and clear, but we cannot see your
ক্যান ইউ সি
slide.
স্ক্রিন? স্ক্রিন এখনো দেখা যাচ্ছে না। আমরা কি এটা তাহলে তোমার যদি সমস্যা বেশি হয় আমরা কি স্কিপ করে পরের প্রেজেন্টেশনটা আগে দেখবো? প্রেজেন্টেশন তো শেয়ার করার চেষ্টা করতেছো কিন্তু এখানে তো
Dr. Adnan, I think we should switch over to the next presenter.
নেক্সট প্রেজেন্টার, হ্যাঁ ওদেরটা একটু
Let him fix this setup.
হ্যাঁ হ্যাঁ। So the next presenter, paper 44, analytical modeling and potential profile verification of p-type cylindrical gate junctionless accumulation mode MOSFET. Presenter নাহিয়ান সাদাত, উপস্থিত থাকলে একটু প্রেজেন্টেশন স্লাইড শেয়ার করে। হ্যাঁ হ্যাঁ। নাহিয়ান সাদাত এখানে উপস্থিত থাকলে আপনি একটু প্রেজেন্টেশন স্লাইড শেয়ার করেন।
স্যার আমি রনি, আমার প্রেজেন্ট দেওয়ার কথা ছিল, ফর্মে আমি ফিল আপ করছিলাম আমরা।
আচ্ছা, এখানে নাহিয়ান সাদাতের নাম কালার করা। ঠিক আছে, রনি আপনি যদি উপস্থিত থাকেন আপনি প্রেজেন্টেশন দিতে পারেন, স্লাইড শেয়ার করে প্রেজেন্টেশন শুরু করতে পারেন।
ইয়েস স্যার। স্যার, ইজ ইট শোয়িং?
হ্যাঁ, স্লাইড দেখা যাচ্ছে, ফুল স্ক্রিন করে প্রেজেন্টেশন শুরু করলে ভালো হয়।
Okay. Hello everyone. Assalamu alaikum. My name is Naitujaman Roni. I, on behalf of my other co-authors, is here today to present our paper number 44. It's on analytical modeling and potential verification of P-type cylindrical gate junction lead accumulation mode MOSFET with stack oxide. In short, CG-JAM with stack oxide. For this device, we assume 2D Poisson equation for solving the analytical model parabolic profile. The simulation device was simulated using Silvago TCAT software. This device aims to help solve short channel effect and provide better electrostatic control and efficiency. We know, according to Moore's law, transistors in a chip doubles in every 2 years, but there are some issues like short channel effects, leakage current, rain-induced voltage lowering like DIBL, gate-induced voltage lowering or GIDL. To tackle these issues throughout the years, many transistors like TFTs, nanowire transistor, multiple gate transistor, all-around transistor, and other transistors were introduced. Our CGAM with stack oxide is a field effect transistor that have cylindrical gate over uniform to have cylindrical gate over cylindrical surface. It is junctionless, so there is no PN junction, and stack oxide is used to reduce the voltage drop and for better efficiency. Sorry. Sir, is it showing?
Yes.
Yes.
Okay, yes. In this paper, we aim to obtain analytical modeling of CG-JAM with stack oxide by solving 2D Poisson equation. Then we aim to simulate the device with Silvago TCATs. Then our analytical model result will be simulated using result plotted will be in Python, and then we'll compare both graphs obtained from simulation software and from Python and find the most optimum value by varying different parameters. For physical model, channel region was assumed to be parabolic, and 2D Poisson equation was solved, and with Gumel-Newton method with constant voltage threshold and Shockley-Ridgel effect model was taken into consideration. We use P-type impurity in the whole device. Here is the parameter table consisting of different parameter of our device. Here we can see that VDS, drain to source voltage, was -1 volt and VGS was -0.2 volt. Here the permittivity of the stack oxide means the higher permittivity oxide, like silicon dioxide that we're gonna use have a permittivity of 25 E0, and channel doping concentration is lower compared to drain or source doping concentration. Here is the 2D and 3D device structure. I will be explaining the structure using 2D structure. Here we can see the gate electrode and SiO2 means silicon oxide and another stack oxide above it. So what's the use of stack oxide? Question comes to our mind. So let's say silicon dioxide thickness is T1 and stack oxide thickness is T2. Then total oxide thickness becomes T1 plus T2. That's all, what we all think, right? But that's not the case. Because of the higher permittivity of the oxide that we are using as stack, like in the parameter table, I show you 25 epsilon naught. It is for hafnium dioxide. Because of the higher permittivity, the effective thickness gets reduced. So even though we see visually it's T1 plus T2, but in actuality is reduced from T1 plus T2 to a smaller value of thickness. For this reason, that resistance across the oxide thickness also reduces. Therefore, the voltage also reduces and the capacitance also increase. The yellow portion represents silicon layer. So why it is called accumulation mode? It is because when we as I shown you guys in the parameter table, we are giving negative voltage. We are giving negative voltage in the gate electrode Vg. Therefore, here because of it is p type, majority carrier is hole gets accumulated near silicon oxide and silicon interface and form a layer from source region to drain region, and current flow from source to drain from this layer. There, as the holes gets accumulated near the interface, this is why it is called accumulation mode. Here's are the equation for our analytical modeling. First, we take 2D Poisson equation that is stated here. And by solving this equation, phi c is we obtain center potential. Here, the expression of A, beta, A, B, and eta is given. And here we have the effective thickness equation and capacitance equation. We can see that EHF is the permittivity of the oxide we are using as stack. From this equation, we can say as the permittivity of the stack oxide increases, the effective thickness decreases. And as the effective thickness decreases, we can say from the capacitance equation, the capacitance increases. So with the decrease of effective thickness, capacitance increases. And when we differentiate the center potential and negatively differentiate the center potential, we get electric field equation. Now let us see the results of our model. Here the scatters represent the simulation result from obtained from Silvaco, and the lines represent results obtained from Python. Black represents stack and red represents without stack. We can say that the center potential means source to drain potential obtained in the center of the device from along the center of the device, center length of the device is without stack is less than with stack. It is because because for stack oxide the effective thickness is less, meaning the voltage drop is less. Therefore, it results in more potential for the same amount of power supply or voltage supply. Then if we see the electric field, we can say that the electric field increases at the drain end. 0 is the source end and 40 is the drain end. We are obtaining result from source to drain. So it is because we are supplying negative VDS voltage. Therefore, as we move closer to VDS, the electric field increases. Then we also varied different stack material like titanium dioxide, and silicon nitride, and obtain the center potential model along source to drain. Sorry. Here we can see that black represents 25 hafnium dioxide, and red represents titanium dioxide, and blue represents silicon nitride. Here we can see that the more the permittivity increases, center potential increases and more is decreases, center potential drops. It is because the more the permittivity increases, I show you in the equation, the effective thickness there decreases. Therefore, the drop decreases and center potential increases. From this, we can say that for the same amount of power supply, we will get more center potential. It can lead us to low power device. Now, figure number 6, we can see that figure number 6, we varied channel length. Here we can see that as we changes the channel length from 40 to 20, the center potential decreases. It is because of the electric field at the drain end, effect of electric field at the drain end. It affects the center potential, therefore the center potential reduces. It is known as short channel effect. And at the figure number 7, we can see that as the silicon thickness decreases, the center potential increases. It is because as the silicon thickness decreases, electrode get closer to center. Therefore, it can accumulate more more hole at the interface of oxide and silicon. Therefore, center potential increases. Now, at figure number 8, we varied the various values of VDS. We can see that as the VDS decreases, center potential increases. It is because voltage at the drain end, negative voltage at the drain end had negative electric field, which affects the center potential. So, lessen the center supply voltage, it lessen the electric field. Therefore, it effect less on put less effect of center potential. Therefore, the center potential increases with the decrease of VDS. So
12 minutes gone, please. Please go to the conclusion. 12 minutes is gone.
Yes, sir. So far from the discussion, we can say that this device can be used to tackle short channel effect and produce relatively low power device, as there is less voltage drop across the oxide layer for stack oxide. Oxide layer for stack oxide. And we in this paper we only work with electrostatics, but there are other rooms of work like current characteristics, DIBL, GIDL. Then we can also fabricate the device at fabrication lab, and we can also obtain values for other high K material for stack oxide. So we also added some references related to this paper. Feel free to check it out if you have any curiosity. And thank you for your patience. And with this, my presentation has come to an end. Thank you, sir.
Thank you, the presenter. If the audience has any question, please come forward and ask the question. We have 1 minute, so we can take 1 or 2 questions. If the audience doesn't have any question, sir, do you have any question?
I have a question to Mr. Ronnie. What is the effect of component density when it will be fabricated on a fiber or fabricated on a wafer? How many gates you can, how many FET you can design on a single wafer? Because the cylindrical gate, it is very difficult to fabricate on a planar surface actually. And it has an effect of the length as well.
Sir, if you don't mind, can you repeat again?
আমি বলছি কি তোমার এই সিলিন্ড্রিক্যাল গেট ডিজাইন করা, ফ্যাব্রিকেশন করা, এটা সিমুলেশন ঠিক আছে, ফ্যাব্রিকেশন প্ল্যানার একটা ওয়েফারের উপরে ডিজাইন করাটা ডিফিকাল্ট। সিলিন্ড্রিক্যাল হবে তো চারিদিকে থাকবে, এটা একটা ডিফিকাল্ট। তো এবং এর একটা মানে চ্যানেলের লেন্থ একটা ফ্যাক্টর, যেটা তোমার প্রেজেন্টেশন থেকে বোঝা গেল। তো এটার কাউন্টের উপরে কি ইফেক্ট হবে তোমাকে আমি জানতে চাচ্ছিলাম।
কারেন্টের উপর কি ইফেক্ট হবে?
কাউন্ট অর্থাৎ ডেনসিটি, কম্পোনেন্ট ডেনসিটি, সিঙ্গেল সাইজ ওয়েফারের উপরে আগে ফেট গুলো চাইতে তোমার ইফেক্ট কত বেশি করা যাবে বা কত কম করা যাবে?
স্যার এটা যেহেতু অল অ্যারাউন্ড ট্রানজিস্টর সিলিন্ড্রিক্যাল, এটার কারণে স্যার এটা সব দিক দিয়েই ইন্টারফেসে আর কি হোল অ্যাকুমুলেট হবে। এই কারণে it will have more control and less leakage current compared to others.
Yeah, performance will be higher, but what about the number of gates formed on a single wafer? Naturally, it will be less, I guess. Okay.
মানে
Anyway,
একটা
that's I
ওয়েফারে
want
তুমি
to have a
কতগুলো
question.
বসাতে পারো?
স্যার ডাবল বসানো যাইতে পারে, মানে আমি তো অল অ্যারাউন্ড একটাই গেট ইউজ করছি, বাট ডাবল ইউজ করা যেতে পারে।
আচ্ছা, ঠিক আছে।
Okay. Thank you for
Assalamu
the
alaikum, sir.
presentation. Yes, so we can go back to paper number 38 if you are present here, Mahmoud Sayyid, simulation and numerical analysis of triple absorber cell using SCAP 1D.
Sir, can you
We are
see
not
the
seeing.
screen now?
No, I am not seeing. Yeah, now it is coming here. Okay.
Okay.
Can you make the slide in presentation mode and start your presentation? Thank you. Please take the slide in presentation mode and start.
First of all, I would like to apologize for the inconvenience that happened. So, hello everyone and good morning. My name is Mahmoud Said, and today I'm here to present my work on simulation and numerical analysis of triple absorber solar cell. So, this work was carried out alongside me, Mr. Shamim Raja and Mr. Dr. MD Mohsinur Rahman Adnan sir from Shahjalal University of Science and Technology. Now, let's have a quick overview of the slides. We'll be going through this presentation. We will then dive into the structure, simulation process, our results, and wrap up the presentation with conclusions. So this is the introduction slide. Now, what is perovskite material? So perovskite material is a thin film solar cell that uses. Why we use perovskite solar cell? So perovskite solar cells recently attracted major attention due to their low manufacturing cost, their high charge carrier mobility, their tunable band gaps. Our main goal, our main aim of this work was to design and optimize a triple absorber solar cell based on perovskite material, that is three absorber layers, and we achieved a high power conversion efficiency by the variation of thicknesses of absorber layers. And while doing so, we maintain the optimal device structure. Now, here is what our device structure looks like. As you can see from here, there the light is coming, and the FTO, that is fluorine doped tin oxide, it is used as transparent electrode. Then we have that electron transport layer. Then after that, we have three absorber layers, that is cesium lead triiodide, CZTSSE, CIGS. And after that, we have spirometer at a whole transport layer. For avoiding complexities, we use a flat band as back contact. So after aligning this structure in SCAP's 1D software, we will get junctional view of the solar cell like this. Now, how we simulated this triple absorber solar cell? So simulation were performed under SCAP's 1D AM 1.5 illumination. Air mass 1.5 illumination means 45 degree. That is, and the light is not going directly or not in horizontally. It's going at an ideal state. And we considered a room temperature 300 Kelvin temperature. And as I said earlier, for avoiding complexities, we used flat band contact. And here's the energy band alignment. So from the flowchart, first I would like to start with the flowchart of the simulation procedure. So when we launch the SCAP app, we click to the set problem. Then we provide input parameters of different layers. Then we provide set working conditions. After that, we specify the action to be measured. then we run the program. By doing so, the SCAPS 1D software has hundreds of equations inbuilt in it, so it can numerically analyze every value of the structure. So this is the energy band diagram proposed for this device. So from this device, the very important thing is that the conduction band of electron transport layer should be lower than the active layer. So for the free flow of electron, and the valence band of electron transport layer should be lower, should be higher for block of holes. Similar case goes for give me a second, sir. So similarly, for spirometed structure, the hole transport for blocking of free electron flow, this will have a higher value, and for free flow of holes, this will have a balance band should have a higher values. So this is the simulation methodology we used. Now, here are the material properties we set for